So this video will be a direct application of isentropic process for ideal gas. In the last video, we have come up with those two equations, and when to use which, it really doesn't matter. You want to find one that works for you for that particular problem. You want to be flexible with it. Okay, so I'm just going to do a quick recap, write down those two equations. So T2 over T1 is equal to V1 over V2, and that's K minus 1. And here I'm actually going to add a little subscript, and here I'm going to write down S equal to constant, which remind me this is for isentropic process, right? Another formula we have, it is T2 over T1. That's instead of volume ratio, we have this pressure ratio, P2 over P1, and it's K minus 1 over K. Okay, so now let's take a look at how do we use it. I have two examples here. The first example said air, well, that tells us it's ideal gas, right? Is compressed from T1 is 22 degrees Celsius and P1 is 95 kilopascal. And it's said it's reversible and adiabatic. In the previous videos, and we're talking about that means isentropic. That means S1 equal to S2. That means it's isentropic process. Okay, so that identify the problem. It's isentropic of ideal gas. Then we can use those two sets of equation. Then they said the compression ratio, volume 1 over volume 2 is 8. So, and we need to determine the final temperature. Now, which one should we use? Certainly this one, right? Because it gives us a volume compression ratio. So in that case, we can go ahead and write down T2 over T1 is going to be V1 over V2, which is 8. Our K value, the specific heat for air, that is showing at our table A2. Okay, for this one, looks like we will be just using 300 Kelvin, right? So if it's 300 Kelvin, our K value is 1.4 right here. So we're going to put that in to this exponent, 1.4 minus 1. Okay, then what do we get at the end? This is going to showing us that's going to be about to be and our T1 value, our T1 value is 22. So we can go ahead and put 22, but make sure you're going to add 273 here, right? And you're calculating this only unknown T2. So T2 will give us 295 times 8 times power of 0.4. Okay. Then that will give us about 665 Kelvin. So that's our final temperature during this isentropic process. Okay, now let's look at a second example. This is a helium. Again, it's ideal gas. It's compressed by adiabatic. All right. And they later told us it's reversible. Again, that tells us it's S is a constant, right? Isentropic process for ideal gas. Initial pressure is 14 psi. And initial temperature is 50 degrees Fahrenheit. And the final temperature is 320 Fahrenheit. Then we need to find out exit pressure. We need to find P2. So go back to those two equations. Which one should we use? We should use this and that, right? Given the pressure ratio. So go ahead and write down that will be T2 over T1 for this isentropic process. That's going to be equal to P2 over P1, K minus 1 over K. Okay, so our T2 is given in 320 Fahrenheit. We cannot use that. We have to change to absolute, which is our ranking, correct? So what do we need to add? So we need to add about 500, no, what did I? 460, okay? So we need to add about 460. So for this T1, which is 50 Fahrenheit, we're gonna add 460 as well, okay? Then that will give us P2, what we're solving. P1 is 14 psi. Then the K value for helium, okay? K value for helium, we can be more precise. We can find the average temperature. So T average temperature will be 320 plus 50 divided by 2. So 370 divided by 2, that will give us 185 Fahrenheit, right? And Fahrenheit, and that will be how much ranking. Do we need to find a ranking? We have to look at the table. So we're going to look at table appendix 2 because it's in US unit. And we're going to go to table H2. So we can use Fahrenheit, and our temperature is 180. So if we have something that's close to 180 here for helium, unfortunately helium is not showing up at table A2 E for B, so we're going to just use we're going to use this 80 Fahrenheit to approximate, and we have this helium right here. Our value is 1.667, so we'll go ahead and use that one. 1.667 minus 1 over 1.667. So when we calculate that, we can find our P2 in a unit of PSI, because this is in PSI. Then they cancel out, right? So the answer we get is 40.5 PSI for the pressure. That's the final pressure for this problem. Okay, so that's the end of this video showing application on how to solve a problem for isentropic process of ideal gas. All right, I'll see you next time on a brand new topic about isentropic efficiency. All right, see you then.